Hello everyone, my name is Dr. Yonglan Song. It's my pleasure to present our work for the International Research Award on composite materials. The title of our presentation is Atomistic Simulation on the Generation of Defects in copper and silicon carbide composites during cooling. Thermal reduced gases will be generated in metal-matrix composites due to the mismatch of coefficients of thermal expansions between components as temperature changes. This will result in stress concentration, non-uniform deformations of materials, dislocations, and micro collapse. Thus, the physical and mechanical properties of the materials should be greatly changed. These issues has long been studied by many researchers, but still have many difficulties and challenges. It is difficult to measure the local stress characteristics in metal-matrix composites experimentally, and the key process of the defect atom scale is unclear. And the objective of our study is to explore the local stress distribution and the types of defects generated in the composites. Also, the mechanisms of defect evolution. And we choose the copper and silicon carbide composites in our study. So these materials have excellent thermal conductivity and electrical conductivity and good resistance. These materials are widely used as engineering materials and various conditions. And this is our composite models in our simulation. The initial model, high temperatures, was built by adjusting the lattice parameters of a single crystal. Then they were relaxed, and then the model was cooled down to 300 Kelvins. And the high potentials was used in our molecular simulations. A slide shows the displacement change of atoms in the composites, and the line 1 is an enlarged view of displacement vectors of the local interface. This picture presents the distribution of stress in both metal and ceramic phase after cooling down from different high temperatures. And the metal and ceramic interface present a higher level of thermal residual stresses. The reference model, the reference model, and only less at 300 Kelvins, and without cooling treatment. Thus, it should be free of thermal residual stress theoretically because of zero temperature drop. And the development of interface stresses is also inevitable due to the interactions between components, between different materials. This model, the model exhibits the highest residual stresses at the interface, and the stresses decrease sharply with distance. This is in agreement with the observations in both experiments and finite element condition simulations that high-level stresses are present at the interface. This picture shows the dislocation network of the composites at the end stage for cooling down from high temperatures. The central sphere are the silicon carbide particles, and the copper atoms have been deleted. The dislocations are distributed along the reinforcement, and the stellar dislocations are also found in the composites. We can see three distinct stages in the development of dislocation densities. First, at the beginning, it is difficult to nucleate, and then the dislocation was rapidly generated, and then they were slowly developing, resulting in a nonlinear relationship between dislocation density and temperatures. Three main possible reasons for the rapid increase of dislocations. First, the large numbers of vacancies in the metal at high temperatures, as we can see in figure B. And second, thermal stresses caused by difference in coefficients of thermal expansions. And the third, the strength of the metal matrix should be decreased, and the lattice become unstable at high temperatures. This picture shows the dislocation network. Shows the typical evolutions of two main dislocations during the uniform decrease in temperatures. They are circular partial dislocations and stellar dislocations. The circular partial dislocations accounted for the dominant dislocation type, followed by the stellar. Other dislocations are hardly found. We found three typical incomplete stacking for tetrahedrons in the composites at the end state of cooling, including the stacking for plate facing the spherical reinforcements is missing. Moreover, the vortex is truncated, and further, the stacking for in one of the plates cannot be found completely. This picture shows the formation process of an incomplete stacking for tetrahedrons in the model, and this is an overview of the defects in the model. And this picture shows the proportions of copper atoms in different structures with temperatures during the cooling process. The stacking for in the phase centrifugal metals occurs in the HCP structures. In the cooling process, the incomplete stacking for tetrahedrons tend to form a stable structure with decreasing temperatures. The figure shows the local structures of an incomplete stacking for tetrahedrons and the stress distribution. And the stress in the metal is not uniform, and the occurrence of plastic deformations leads to relaxations of formal stresses. And there are some limitations in our study. First, an ideal single crystal machine model was thought in the simulation, which may lead to a difference between the dissolvable and experiments and the finite element simulation. And second, the generations of formally reduced stresses and the micro defects in mathematical composites are complex issues. There are many other factors that may play a role, which needs to be further studied. Third, and the most potential, the parameters may be insufficient to capture the complete information of interface bonding. Several conclusions can be drawn in our study. First, the evolutions of dislocation explains free mainstays are difficult to nucleate, rapid generations, and slow development, resulting in non-linear relationship between dislocation density and temperature. And the second, the circular partial dislocation accounted for the dominant dislocation type, followed by the stellar dislocation. Others are harder found. And the third, the incomplete stacking for the features with various shapes and sizes were found around the reinforcement. Fourth, the immobile stack law dislocations as well as the highly stable incomplete stacking for tetrahedrons serves as a barrier to the further development of plastic deformations in the metal matrix. And that's all. Thank you for attention.